Hello, ib2 students. Still, we're doing chapter 8, energy production. Okay. Still, we have to do one small topic related with greenhouse effect. So at the beginning, thank you for your test. Remember next time, okay, please connect all your photos or pages into one PDF file, okay. You can use jpg2pdf.com website. Then in an easy way it is able to connect your pictures into one PDF file, but still my recommendation is to write on the computer. You can open this PDF file in the Acrobat Reader and write your answers directly on the computer. It's not a problem with making a copy, making a photo. Okay, so short revision of our last lesson. We're talking about energy balance. First, we've calculated power of the sun. Do you remember? Power of the sun is related with sun's temperature by Stefan-Boltzmann law, assuming that emissivity of the sun is equal to 1, so it behaves as a typical black body. We can calculate power of the sun if temperature of the surface of the sun is known. Okay? Then we've used power of the sun and calculated intensity of radiation at the upper parts above Earth's atmosphere at the place when Earth is located by using inverse square law of radiation. In this case, this small r is average distance between Earth and the sun. Okay, and this factor, which is constant because power of the sun is constant and average distance between Earth and the sun is constant, is known as a solar constant, and solar constant value is given in your data booklet is around 1400 watts per 1 square meter. Okay, then we've used solar constant and calculated intensity of radiation absorbed by Earth's surface. We've used albedo in this factor of 4. I've explained this factor 1 of the 4. It occurs here because surface area of the Earth is 4 times bigger than surface area covered by, in average, by sun's radiation. Area of the sphere is 4 pi r squared, area of the circle is pi r squared, so the factor is 1 over 4. Of course, we have to subtract part of radiation which is reflected, scattered, albedo, and we've used this solar constant, and we've calculated the intensity absorbed by each 1 square meter of the Earth, and by using energy balance, that intensity which is absorbed is equal to energy intensity which is emitted. Assuming that Earth behaves as a black body, we've calculated temperature of the Earth. Emissivity is equal to 1. We've assumed that Earth behaves as a black body, and we've obtained temperature around 255 kelvins or something like that, which is a very, very good approximation. Is of course around 31 or 32 kelvins or degrees Celsius less than actual average, but we didn't take into account many factors, like the fact that Earth contains an atmosphere. Okay, so today we'll be talking about greenhouse effect. So please prepare to the lesson notebooks, pen, pencil, ruler, maybe calculator, and of course your Tsokos. Tsokos page number 335. Okay, and 335 Tsokos you have this topic, and this is the last topic in this chapter, so it's not too long. So at the end I give you some parts of the material to review, some exercises to calculate, because after the break, so at Thursday lesson is not obligatory, and Tuesday is also not obligatory, so we will spend one more lesson with revision, so Thursday and Tuesday in 2 weeks. Today is 7th, so 21st. I will write a post to you, but around 21st of April it will be major test on energy production. Okay, but today's topic is greenhouse effect. Okay, I hope that you know what the greenhouse effect is. Probably you did this during your English course in middle school, during your English course in high school. I'm sure that you did this on the geography and maybe on the science. In general, you know what the greenhouse effect is. But the idea is to understand it in terms of physics. Okay, so let me first describe it, and then we will make a kind of note. Yes, so let's look. This is the surface of the Earth, and Earth is covered by the atmosphere. The thickness of the atmosphere is around 100 kilometers. Of course, above we can find some particles. 500 kilometers above the Earth we can find some particles. But let's assume that the thickness is around 100 kilometers. Okay, and of course Earth is illuminated by radiation from the sun. So this is sun far, far, far away, and it emits radiation towards the Earth. And let's focus on the part of radiation which falls on the atmosphere. I'm not interested I'm not interested fact that part of the radiation is reflected by the atmosphere, is absorbed by the atmosphere, is reflected by the atmosphere or is reflected by the Earth. I'm interested today only part of radiation which travels through the atmosphere. Okay, so this radiation has a specific wavelength. Of course, this is the range of wavelengths, but I hope that you remember that temperature of the sun, okay, Ts, is around at the surface 5800 kelvins, and for this, by using Wion's law, we've calculated the maximum, no, maybe not maximum wavelength, but wavelength of maximum intensity. We've named this lambda max, and it was around 500 nanometers. Okay, and 500 nanometers corresponds with yellow color, and this is why sun is visible as a yellow. On your data booklet you have this, okay, I'm talking about this. Lambda max, so wavelength for maximum intensity, is related with temperature in kelvins by this factor 2.9 times 10 to the power of minus 3. So if you know temperature of the object, you can calculate its wavelength of radiation which is emitted the most. Okay, so maybe I'm going to write this somewhere, that lambda max in general is related with temperature in kelvins by factor 2.9 times 10 to the power of minus 3. Okay, so if bigger the temperature, if higher the temperature, then shorter the wavelength, and vice versa. If the wavelength longer, then smaller the temperature. Okay, and this radiation, okay, travels through the atmosphere, and because travels through the atmosphere, just this. Of course, part is reflected by the atmosphere, but we are not interested in this. Okay, and this radiation is absorbed, and again, not at all. Part is reflected by the Earth's surface, but we are interested only in radiation which is absorbed by the Earth. Okay, and due to this radiation, Earth is heated up. Do you remember temperature of the Earth is more than 250? In reality, is more than 280 kelvins. So Earth also absorbs or re-emits this radiation. Okay, so Earth is heated up and emits this radiation. We used this energy balance last lesson. So this red arrow represents, in this case, this red arrow represents radiation re-emitted by the Earth. This is absorption process, and red arrow is radiation re-emitted by the Earth. Okay, this orange one is radiation emitted by the sun. Radiation emitted by the sun. Okay, and what is very, very important here? Important is that sun has completely different temperature than Earth. Okay, Earth's temperature is around 280 kelvins. Yeah, or we've calculated 255, so let's use value from our model. Earth's temperature calculated was 255 kelvins. If Earth's temperature is different, so what happens with lambda max? Lambda max, so wavelength of radiation emitted by the Earth, is completely different than wavelength of radiation emitted by the Sun. Okay, so if Sun has lambda max as 500 nanometers, then we can calculate, of course, lambda max corresponding with 255 kelvins. But what is important, if temperature of the Earth is much more smaller than temperature of the Sun, then the wavelength of the most intense radiation will be much more bigger. Okay, so the idea is that if temperature of the Sun is bigger than temperature of the Earth, and it is because Sun's surface has 5800 kelvins and Earth's surface has 255 kelvins due to our model. So in lambda for the most intense radiation of the Sun is much more less than lambda for the most intense radiation for the Earth. What does it mean? It means that radiation which is re-emitted by the Earth is much more longer than Sun's radiation. I'm going to write this short wavelengths, long or longer wavelengths for radiation emitted by the Earth. Okay, and this is important because if radiation travels towards the Earth, okay, then wavelength is short. If radiation travels away from the Earth through the atmosphere, then radiation is long. Okay, so this is very, very, very important, the most important here, that wavelength of radiation which travels through the atmosphere from Sun to the Earth is short, and wavelength of radiation which travels through the atmosphere emitted by the Earth, so from Earth towards the space, is long. And what happens now? In the atmosphere, we have a group of particles called greenhouse gases. Okay, it's nothing special. In general, greenhouse gas is a molecule, okay, which is able to absorb long radiation which travels from the Earth and is not able to absorb radiation which travels from the Sun. Okay, so practically, greenhouse gases are transparent from radiation traveled from the Sun and not transparent from radiation traveled from the Earth. So this radiation, which is re-emitted by the Earth, this long wavelength radiation, is absorbed by the greenhouse gases. There is no absorption of radiation from the Sun because it's too short. About absorption, I'll give you more details on next slide. So let's look. If there is a absorption, so there must be also emission. Okay, so this emission, which is absorbed by greenhouse gases, is emitted, but in all directions. What does it mean? It means that part of this radiation travels back towards the Earth, okay, and heats up the Earth again. Is it clear? So again, Sun emits radiation which is short. This radiation passes through the greenhouse gases. There is no interaction because it's too short. This radiation heats up the Earth, is absorbed by the Earth. Earth, due to the energy balance, emits this radiation, but due to the fact that temperature of the Earth is less than temperature of the Sun, this radiation re-emitted by the Earth has longer wavelengths due to the Wion's law. Okay, and this long radiation interacts with the greenhouse gases in the atmosphere. Okay, so there is absorption of this radiation. If there is absorption, there must be emission. This radiation absorbed by greenhouse gases is emitted in all directions, and part of this radiation heats up Earth again. And this is known as a greenhouse effect. Oof! I hope, do you understand this? If not, please move the movie back and watch it again. Now I'm going to give you in a few points the most important details about this effect. Okay? So let's write something like this. We are talking about greenhouse effect. Yeah? So write bullet point number 1. Sun emits radiation of wavelength around 500 nanometers because its temperature is around 5800 kelvins at the surface. Yes? Okay, next. This radiation passes through the atmosphere. Of course, part is reflected by the atmosphere, but in general, it passes through the atmosphere. Atmosphere. And heats up the Earth. And again, part is reflected by the Earth, but we are interested only of heating process, and heats up the Earth. You can write is absorbed by the Earth. Okay. Next, Earth re-radiates this radiation. Earth re-radiates this radiation, but due to the fact, but maybe of longer wavelengths, Longer means infrared, not 500, not visible, but infrared. Okay, because Earth's atmosphere, Earth's surface is colder than Sun's surface. Okay, and the name of the law is Wion's law, and this law is this one. Oh. Okay. Move it into back, a little more up. Next, radiation re-emitted by the Earth. Emitted by the Earth. This longer one, yes, longer. In the case of wavelength, this radiation is absorbed by greenhouse gases in the atmosphere. Okay, about absorption, a little bit more details on next slide. In the atmosphere, and is re-radiated in all directions. Okay, in all directions means that part of this radiation heats up Earth again. Part of this radiation heats up Earth's surface again. Okay, oof. And here you have short description of greenhouse effect. So short radiation emitted by the Sun travels through the atmosphere, is absorbed by the Earth. Earth re-emits this radiation, but due to the Wion's law of longer wavelength, and this radiation of longer wavelength interacts with greenhouse gases, is absorbed by greenhouse gases, and re-emitted by these greenhouse gases in all directions, part towards the space and part towards the Earth again. So finally Earth is heated up by the same radiation again. So this is why temperature of the Earth is bigger with the atmosphere than in the case without atmosphere. Very good example. Earth and Sun. Earth and Moon. Okay. Solar constant for Moon is almost the same as solar constant for Sun, because Moon is in almost the same distance from the Sun than Earth. And what happens on the Moon? The temperature is around 30 kelvins. The average temperature is around 30 kelvins less than the temperature of the Earth. Moreover, we have huge difference between maximum and minimum temperature at the surface of the Moon. At the day, the temperature is very, very high. At night, the temperature is very, very, very low. In the case of Earth, which is covered by the atmosphere due to the greenhouse effect, the changes of temperature between day and night are not so significant. And of course, average higher temperature is bigger by around 30 few kelvins than the case without atmosphere. Okay, please copy this And the next slide will be about greenhouse gases, and next about the mechanism of absorption of energy. So stop video, copy this, and turn it back when you'll be ready. Okay, so what are greenhouse gases? Okay, are gases which are able to absorb radiation emitted by the Earth and not able to absorb radiation emitted by the Sun. So write this. Greenhouse gases are able to absorb long radiation, long wavelength, long lambda radiation re-emitted by the Earth or other words are not able to absorb short radiation, short in the case of lambda, short lambda radiation emitted by the Sun. Okay, in Tsakos on page number 336 you have table with greenhouse gases or sources of greenhouse gases. So you have to know this table. Let me talk a few words about this. So we have four main greenhouse gases. Okay, is here CH4. Okay, N2O, O2, and H2O. Okay, so here H2O is of course water, and natural source is evaporation from oceans, rivers, and lakes. Okay, and anthropogenic sources is irrigation. Okay, due to the irrigation we have also more surface covered by the water, so bigger evaporation. Okay, O2, so oxygen, forest fires, volcanic eruptions, evaporation of water from oceans, yeah, and O2, it should be CO2. Yeah, it's O2, CO2, carbon dioxide, next CO2. Okay, forest fires, volcanic eruptions, evaporation of water from oceans, and anthropogenic sources. Carbon dioxide is burning fossil fuels in power plants and cars, burning forests. Okay, you know that in this book there are a lot of mistakes, but this is very significant mistake. Not O2 but CO2, remember. Yeah? Okay, next. CH4, methane, wetlands, oceans, lakes, and rivers, and anthropogenic sources, flooded rice fields, farm animals, oh this is important, farm animals, processing of coal, natural gas and oil, burning biomass is the source of CH4, and last one, nitrous oxide, N2O, forest, oceans, soil and grasslands, and anthropogenic sources created by humans, burning fossil fuels, manufacture of cement, etc., deforestation, etc., etc. So you have to know the names of these four: H2O, water vapor, CO2, carbon dioxide, CH4, methane, and N2O, nitrous oxide. You have to know minimum one natural source and minimum one anthropogenic source. Anthropogenic means created by humans. Okay? And last slide, please copy this. Yeah, and you will be ready. Turn the video again. And last slide about mechanism of absorption. In your Tsakos is known as the mechanism of photon absorption, probably. Yes, mechanism of photon absorption, 337. Page number 337. So how are photons emitted by the Earth absorbed by the greenhouse gases? You know that molecules, similarly to atoms, have discrete energy levels. Okay, these energy levels are related with translational motion and with rotational motion, in general with vibrations. Okay, and you also know that each radiation of a given wavelength has a certain amount of energy. Yes, higher level students know that this energy is described by the equation h times f, or hc over lambda. So each photon of certain lambda has a certain amount of energy. So we can calculate energy of photon emitted by the sun. In the case of sun's radiation, lambda temperature is high, lambda is low, so energy is high. And we can calculate energy for photon of infrared photon emitted by the Earth. Temperature of the Earth is low, lambda emitted by the Earth is high, so energy emitted by the Earth is low. Okay, and the greenhouse gases. These molecules from the group of greenhouse gases have energy levels, difference in energy levels, which corresponds with energy of infrared photon emitted by the Earth. Okay, so we can write that infrared photon emitted by the Earth has energy which corresponds with difference between energy levels, between discrete energy levels, of greenhouse gas molecule, of greenhouse gas molecules. Okay, what does it mean? It means that photon of this particular wavelength is absorbed by this particular molecule. Okay, so these photons are absorbed by molecules of greenhouse gases, by molecules of greenhouse gases. Okay, so why does photon emitted by why doesn't photon emitted by the sun absorbed? Why? Okay, photons emitted by the sun are not absorbed. Why? Because different wavelength means different energy. So this energy of photon emitted by the sun doesn't fit to the difference between energy levels of greenhouse gas molecules, so it's not absorbed. Photons which have different energies pass through the greenhouse gas molecules. Photons which have accurate energy are absorbed by greenhouse gas molecules. Is it clear? Okay, and moreover, if this, you know that when molecule absorb photon, then it is promoted to higher energy level. But molecule cannot be excited all the time. So when energy level of greenhouse gas molecule decreases, then what happens? Then this energy is released. Then this energy is released. In the form of photon, of course. In the form of photon, which is emitted in random direction. Is it clear? This photon can be emitted back to the Earth. Okay, it is released in the form of photon, and some of these photons travel towards Earth. Some of these photons travel towards the Earth. Okay, so here we have quite precisely described the mechanism of this photon absorption by greenhouse gas. All depends on the energy, which depends on the wavelength, and wavelength depends on the temperature of the source, and this is the key. Sun short wavelengths, different energy. Earth, long wavelengths, different energy, and these energies emitted by the Earth are the same as discrete energy levels, a difference between discrete energy levels of greenhouse gas molecules in the atmosphere. Just this. Okay, so please make notes. So you have to know what the greenhouse effect is, you have to know some greenhouse gases including sources, and you have to know the idea of photon absorption by greenhouse gas molecules. Okay, and let's back to Tsokos. We finished chapter. Okay, so now we are ready to do some exam style questions. So your homework is Tsokos 340, 341. Okay. Okay, exercises from 1 to 10, MC questions, multiple choice questions, plus one exercise related with calculations, mainly with this. Okay, black body radiation, and exercise number 14 on page number 344. So Tsokos 344, exercise number 14. Okay, our next meeting is obligatory meeting is next week, so please do this on next week. Don't send me your answers. I give you answers by additional file. We'll be talking about this by Google Classroom. Remember, in 2 weeks, a kind of major test at Thursday. Meeting is not obligatory, but some of you wants to see me or hear me and see my handwriting. So I will prepare something. Calculations, not obligatory, so I cannot introduce a new material. Okay, thank you for watching. Again, any comments, write in Google Classroom or as a comment below this movie. So, learn physics, stay at home, good luck, and see you. Bye.